Hello everyone, good morning. JP here from Advanced Organic Chemistry. Today we're going to start a new unit. We're going to look at something called the Michael reaction, and specifically we're going to be looking at something called conjugate addition. So a lot of this stuff can be found in chapter 22 of your textbook. So let me just take a few moments and write down the outline over the next couple of lectures. Conjugate addition. In our case, we're going to be talking about the Michael reaction. Chapter 22. So first we're going to talk about the Michael reaction. We'll spend a lecture on that, talking about the differences between 1,2 addition and 1,4 addition. We'll talk about the energetics. Later on, we'll talk about things like soft versus hard theory and how that can help us predict and control the Michael reaction. And as you may have thought and predicted, we're going to look at specific enol equivalents and how we can apply those to the Michael reaction. And then we'll look at some specific examples later. So I won't put those in right now. So let's focus on the first part, the Michael reaction. Okay, so this type of compound here is what we call an alpha-beta unsaturated carbonyl compound. So this is your alpha carbon. That's beta, so alpha-beta unsaturated carbonyl. And these compounds are quite special because you can imagine a nucleophile. Let's make that a negatively charged nucleophile. The nucleophile could attack the carbonyl, as you've learned and seen many, many times in this course. So that's one route of attack, or another route of attack could be the same nucleophile attacking the beta carbon because it is in conjugation with that carbonyl compound. So you have two entries for attack. Now, we call this, if we have this reaction occurring, it's blue arrow, but you probably can't see that it's blue. If you get reaction occurring at the beta carbon, we call that Michael addition. Okay, so if our compound here, let's just add a compound, and let's say we wanted this to react with this compound at the beta carbon, we want this to occur through Michael addition. We would want to find some way to enolize this compound, and then this would come and this would react right here as I'm showing you. Electrons would go up and so on and so forth. So we call this reaction here, or this part of the reaction, the Michael acceptor. And we call this part of the reaction the Michael donor. So if these two molecules come together, they will look like this. So R1. And because the electrons will come here, move here, you're going to be left with an enolate on this side, R2. And then this will pick up a proton, so you'll generate a compound with two carbonyl compounds. So we often call this the Michael product. And the Michael reaction is a very useful way for making compounds with two carbonyls. We've seen that already with things like the Claisen condensation. Aldol reaction is a great way to make carbon-carbon bonds. This also makes, obviously, carbon-carbon bonds, but these compounds with two carbonyl groups can be very useful molecules for organic synthesis because it can lead to a pathway of a variety of different products. So Michael reaction is a great way to make molecules with two carbonyls. Okay, so there's your little intro to the Michael reaction. So let's talk a little bit more specifically about how we can generate the desired Michael product. So let's go to this board here. And let's say we want to make this compound. Okay, so R prime, R double prime, R, this is R triple prime. Okay, based on what we saw over there, how could we make this compound using a Michael acceptor, Michael donor approach? What would those starting materials look like? Okay, so you can see here that you have an alpha, you have a beta carbon potentially, and then over here you have another carbon, we'll call alpha prime. So if we construct this, we have two different ways we could put this together. Right, you could imagine that we break it up over here, where this is the key carbon-carbon bond. This portion here would be your Michael acceptor. This portion here would be your Michael donor. So why don't we call this scenario A? So scenario A would have this as your Michael acceptor plus your Michael donor would look like this before it enolizes. Okay, so before we start thinking about what reagents we'll use and what conditions, again, like we often do in organic synthesis, you have to find that key carbon-carbon bond and isolate your two starting materials. Okay, Michael donor, Michael acceptor. So that's one way to make it. The other way to make it is if you look at scenario B, where you cut it here, and on this side of the molecule will be your Michael acceptor, on that side will be your Michael donor. There's your Michael acceptor, your alpha beta unsaturated carbonyl compound, and then our Michael donor will be this here before it enolizes. Okay, so both look like valid approaches, and in theory and on paper they both look viable and they both should work. However, what we'll learn today and over the next few lectures is that there is, one way that's going to work a lot better, kind of similar to how we learn with aldol reactions and Claisen condensation, and that's really going to impact what those different R groups are, so that you can get your desired Michael product. So before we talk about the desired Michael reaction, let's talk a little bit about specificity. So let me get my marker. And as I mentioned up here on the first reaction, you can see that you have a competing reaction where the nucleophile could react at this position here, and we call this direct addition. So maybe I'll write that here. We call this 1,2 direct addition. Okay, and the reason it's called 1,2 is because we have number 1, 2, and then we can keep going 3, 4. So if you're actually doing the reaction through the Michael reaction, it's actually 1,4 conjugate addition. Okay, so let's talk about how we can control selectivity. Okay, so here's your here's your Michael acceptor, and then let's draw an enolate here, which will be our Michael donor. And the desired reaction, of course, is where this comes here. This reacts, and then you get this compound, just like I'd done up there, and then this will pick up a proton. Okay, so that's one pathway, and then the other pathway is if you take, let's say, the same enolate, and I think what I will do is I will have this attack through the competing reaction. So this can now attack here, and then the electrons can go up. So if that happens, this is going to be called direct addition. And your compound will look like this through the direct addition. And then what will happen is that this will pick up a proton, and you will generate this compound. Right, which is actually the aldol reaction, right? We've created an alcohol with a ketone or aldehyde. So that's simply aldol reaction. So direct addition would lead to this compound. So how do we understand and control, in our case, the Michael addition, which is on the left? Let's first take a look at both of these structures before they get protonated to give the product. So when this compound, this enolate, reacts, we generate this enolate here that has a double bond. When we do direct addition, we also get a structure with a double bond here. Question to you is, which compound is more stable? This double bond here that has 1, 2, 3 substituents, or this double bond that really just has one substituent? So the one that's more substituted is going to be more stable, right? So let's call this the thermodynamic pathway. Okay, more stable, more substituted. This direct addition actually leads to a less stable compound here, and we call this the kinetic pathway. It will form faster, however. So one of the things we can do to try to ensure that we get the thermodynamic pathway in this reaction is to ask ourselves this question. During this reaction here, is it possible to undergo the reverse reaction? So before this proton gets picked up, is it possible for the electrons to come back down here and then reform this enolate. Because if you can do that, then you increase the chance of it actually going to the thermodynamic pathway. So what we want to do if we're doing the microreaction is we want to increase the likelihood of reversibility of that 1,2 direct addition so that we increase the chances of making our 1,4 conjugate addition product. Okay, you can think of this as being fairly irreversible, okay, but it requires a little more energy. So to increase the likelihood of the thermodynamic product, we need to increase the reversibility of the 1,2 addition pathway. So right down at the bottom of this board here. Hope you can see it. I'll read it to you. To increase the likelihood of the thermodynamic product, need to increase, that's right, we need to increase the reversibility of 1,2 addition pathway. Okay, so let's look a little bit at the energetics of the Michael addition reaction. So let's take a look at an example here. Let's take a look at if we take this carbonyl compound with an ester, and then if we react this with a Michael acceptor, and the question is, well, if we enolize here, right, which should be fairly straightforward because you have proton between 2 carbonyls, pK will be around 13 or so, and then this carbon anion will react here. Okay, so if we do that, our product is going to look like this. And let's take a look, and I'm just going to number a couple things here. We got carbon 1, carbon 2, and let's call this carbon 3, carbon 4, so we can see exactly where we are carving and making those bonds. Okay, so let's look at the energy of the bonds that are going to break. Okay, so we have this carbon, this double bond here, C3C4. So let's actually calculate the energy of that double bond. Turns out that the C3C4 is around 146 kilocalories per mole. Now the C2H bond, okay, over here, you're going to replace it, will change, but you're going to actually form now a CH4 bond. Okay, so that will cancel out. So we don't need to worry about C carbon-hydrogen bonds. Energy of bonds that will form. Okay, so during the course of this reaction, we have made a new sigma bond. Okay, so here we're taking into account the double bond. So here now we have a sigma bond, so C3, C4, sigma bond, that's around 88 kilocalories per mole. And what we've also done is we've created this new carbon 2 carbon 3 bond, which is a new carbon sigma bond. This one is around 85 kilocalories per mole. So if you actually add that up together, that is 173 kilocalories per mole. So if we look at the delta H, the heat of formation for this reaction, what we're going to do is we're going to take out the sum of the bonds that are broken minus the energy of the sum of the bonds that formed, and that should give us the amount of energy necessary for this reaction. So let's plug in our numbers of bonds that are broken. So that will be equal to 146 minus 173. Okay, so that's going to be sort of around, okay, so I'm just ballparking it here. That's going to be around minus 30 kilocalories per mole. Okay, so this is an exothermic reaction. Okay, heat is released during this reaction, so it's a very favorable reaction, and it's our thermodynamic product and pathway. Let's take a look at the energetics of the Michael reaction if we actually do direct addition. That is the undesired product in this case. So I'll be looking at this reaction here. So how about I'll erase up here. So energetics of direct addition. And we can look at the same two starting materials in this case, in this study. So if we get direct addition, that would involve this carbon nucleophile reacting at this carbonyl here. So what your compound will look like is it will look like that. Okay, so let's do the same thing. Let's look at the energy of the bonds that will break. Okay, so what we're doing is we're breaking a carbon, this carbonyl oxide, this carbonyl group here. So this is around 180 kilocalories per mole. And the bonds that will form, we're forming a new carbon-oxygen bond and a new carbon-carbon bond. So the carbon-oxygen bond is 85, around 85 kilocalories per mole. And then this carbon-carbon bond here is around 83 kilocalories per mole. So if you add these up together, that's around 168 kilocalories per mole. So if you apply that same formula that we did before, and look at the delta H of formation for this reaction, take the sum of the bonds that will break minus the sum of the bonds that will form, okay? So same formula, bonds broken, okay, minus bonds that will form. So the bonds that are broken, that will be 180 minus around 168. And again, we always sort of ballpark these numbers as organic chemists. So this is around 10 kilocalories per mole. So you can see here that this is actually not exothermic. You actually have to put some energy into the system. And it sort of makes sense because you are generating that kinetic pathway, which leads to the less stable complex. Okay, but nevertheless, the energetics do favor Michael addition over the direct addition from an energetic point of view. Okay, as I mentioned, the conjugate addition reaction is formed by increasing the likelihood of this reversibility. So let's think about what we could do to make that more reversible. So I'm trying to decide which board I should erase. Let's try up here. And I think what I'll do is I'll put this in a neat little box because we might use that again for the next lecture. So conjugate addition is formed by increased likelihood of the direct reaction being reversible. Conjugate addition is favored when we increase the reversibility of 1-2 addition, direct addition. Okay, so let's see what forms or what tricks we can use in order to do this. So since I have it here, let's see what we can do to increase this reversibility. And I want you to think of what these R groups could be or should be for that reaction. So maybe let's start with the enolate. If this enolate comes and it reacts through direct addition, and we want it to go back so we can eventually get a product, what kind of groups do you think you want to put as R2? This is going to depend a lot on the stability of this, right? So if this thing is fairly stable, it's going to be happy going through the reverse reaction, right? But if it's not very stable, then it's going to get stuck in the kinetic pathway. So with respects to the enolate, we can control this by 1. Increasing the stability of the enolate. And the enolate is negatively charged, so if we think of adding something that can stabilize a negative charge, something like an electron withdrawing group, that would increase the stability and therefore its reversibility. So let's place and put an electron withdrawing group at R2. Okay, what other thing can we do over here? Let's think about R1, our electrophilic center. So what other tricks can we do? R1 is going to play an influence for sure. R1 could be very small like an aldehyde, and you know that's really electrophilic. If you start adding carbons or some bulk here, that reduces the electrophilicity. So we can control the desired 1,4 addition by making R1 in this group here a little less electrophilic. So let's say modifying R1 on electrophile to make the carbonyl less electrophilic. Okay, and then the last slide I have for today is, again, just emphasizing how we can control this thermodynamic reaction. So thermodynamic control is favored by, as I mentioned, adding electron withdrawing groups to the Michael donor. Sometimes we like to add, 2 electron withdrawing groups to really stabilize it and make it a strong, stable, healthy enolate. The Michael acceptor is activated by things like esters, amides. Okay, so you imagine if you have an ester here or an amide, that's really going to reduce the electrophilicity at that carbonyl. Or even think of R1 and big bulky groups there, right? Put like these terbutyl groups or whatever it is so that you can't get attacked. And as I mentioned, you really want to avoid aldehydes, and if you can, ketones as well. Okay, so I'll give you sort of some examples here. This compound here would probably be the worst Michael acceptor, right? Well, not the worst, but not great because you have an aldehyde here. So you're really going to get a lot of direct addition. Okay, so that's going to be not so good. The next one after that would be something like a ketone. As soon as you start adding esters, you now know that electron density will go into that carbonyl, making it less electrophilic. And then you have things like amides. And then other types of groups, they don't always have to rely on carbonyls. As long as you have something that's electron withdrawing and it's conjugated, things like nitrils are good. So as we go from left to right, you decrease the electrophilicity at that direct addition carbon and thus increase the likelihood of conjugate addition. And then there's one more thing, number 3. So I'll write that on this board here. Oh, here's my marker. Okay. And then number 3. Okay, so let's think about the electrophile. We've already talked about making this like esters or bulky, but what about this portion of the molecule? So if you want this reaction to occur at this carbon here, you want to keep this unexposed as much as possible. So you don't want to put a lot of bulk here because then you're going to have steric clash and it's going to be hard to get reaction occurring here. So I'll show you exactly what I mean. 3. So the Michael acceptor has no substitution at the beta carbon. So this compound here would be better compared to something like this, which would be better than something like that. Okay? And it makes sense because you're starting to block the site as soon as you put some steric block on there. Okay, I hope you enjoyed this first introductory lecture focusing on the Michael reaction and understanding the energetics and how we can try to control its reaction. We're going to start talking about some specific examples soon, and then we're going to also talk about soft versus hard theory, and then as it shows there, moving on to specific equivalence. So see you soon for the next lecture.